So, and it's nice to see. Thank you. Okay. Do I have to speak into this for the? Are there anybody online? Nobody's online. Or?
Yes, there is one person online.
Okay. Anyway, nice to see that there is. Good morning. Nice to see that there are other intrusions that have not been investigated for a long time, and there's still work to be done. And I'm going to present something similar here. This is my first time at the Wager and Brown workshop or any like that. It's because I mostly work on mafic dikes and minor intrusions, which is preferably to get the magmatic composition of things, which is something that is difficult for the layered intrusions. But I have come across some now here, and luckily I could get it presented. And I think it's quite special because it has this substantial downward accumulation, whereas you often get accumulations from below or upwards in most cases. And it is quite a rare layered intrusions in the Karoo large igneous province, which mostly hosts sills, and some you will present later, Steve, on some layering inside some of these sills, but it is quite rare to find these. Okay, let me move on. So I'm gonna start in a little bit of a broad picture here. Maybe it's easy to look here. Here are two large igneous provinces, the North Atlantic here where we are, and then the Karoo large igneous province, about 3 times the age ago. And I don't want to digress too much into these, what these large igneous provinces are, but I'm going to emphasize that we have the Skagerrak intrusion. Everybody knows that. And its location inside this large igneous province is very much in the center, which is also the most magmatic part, and where the breakup has been. Both of these are breakup lips, and they are where you have this conspicuous bend in the breakup here in the Skagerrak. And I think we have the similar setting for the Mwenetsi complex that we're going to get to, very much in this bend where you have the Lebombo and Mwenetsi monoclines. And there's been many comparisons between these two rifted margins. And the similarities are really striking. So it's quite cool that we have a layered intrusion, a very rare layered intrusion here, which shares the same tectonic setting as the Skagerrak intrusion. And I've been so bold as to actually saying that they have, very much the same setting. So this, but this in comparison to the Skagerrak, which has been investigated intensively, this one has not been investigated since the 1960s, right, by the legendary Keith Cox and his co-workers, a pioneer, Keith Cox, in the understanding of the Karoo large igneous province, and they produced this magnificent map. And since then, very little has been done on this. And you can see that there are several intrusions here, and as well as some granophyrics, so a lot of felsic rocks here in pink, as well as some felsic lavas, younger lavas that lie on top of these basalts. They're all intruded or down sagged into this basalts here in green. And in amongst these, you have some mafic intrusions as well, which are a little bit older and a little bit disturbed. And the northern one of this here is the one that appears to be the best exposed and shows the most magnificent layering. In Google Earth, you can see the fertile soil from the mafic rocks, providing some agriculture there, whereas the granophyres surrounding it is much more bushland and not as fertile. But anyway, this intrusion has been studied by one of the co-workers, which was Christopher Stillman, I think. I'm not sure if he did it for his PhD, but he produced this publication here of the mapping and the structural relationships and how it was in cross-section and in plan view, and also produced this stratigraphical log. So they did have thin sections and did some petrography, but unfortunately he never published the results from these. And I think the thin sections have since been lost. I've just spoken with him. He's retired now in Ireland. But this is how it is. And I agree with these, the sort of cone-shaped geometries, ring-like, almost like cone sheets, but in geometry, and because the dip of the layering or the igneous lamination here is pretty much 36 degrees along this section that we've done here. So I went on 2 Cs. So before that, in this paper, he comes up with an interpretation on how this intrusion of the layering has come about, and he proposes that there are 4 intrusions into the same kind of body in succession, mostly starting from below. So you have your gabbronorites in blue here, and then you get another injection of magma which forms a basal olivine-rich olivine gabbro, overlain then by gabbronorites again, and then not continuing on top again, but rather the top one gets emplaced, maybe a little bit strange, mainly crystallizing the basal layer and might be overlain by some gabbronorites that has since been weathered away or eroded away. And then he sort of proposes a little bit strange that there was an injection, like a sill-like injection into this cumulate pile as a G4 here, again forming a gabbroic basal layer. And I think the arguments for that is that you have some igneous lamination. But anyway, that is model. That's how he thought this intrusion was formed at that time. We I forgot as well. There's a granophyre that intrudes later as well, which is quite important here, that I want to emphasize. Anyway, we went back for 2 field seasons, collected 60 cumulate samples along this riverbed. So I guess one of the other reasons why it's not so investigated is it's relatively weathered, but you can find in situ rocks along these dry river streams that we have here. And we collected 60 cumulate samples along here, plus 3 chilled samples along the margin, pretty certain about that. And we also collected some dikes that intersect or have a direction trend towards the intrusion, which could potentially be feeder dikes. So we have some control on the parental magmas for this intrusion. So in comparisons to their log, this is our log, the second log here to the right here, from what we've seen in this riverbed. And here are all the thin sections, the scanned images of these, and the log again just enlarged to show where these thin sections are shown. We also show some grain sizes here, compiled, and other features. Can I just get rid of that one? Okay, thanks. Anyway, well, we're going to go through this log here now from top to bottom. So in many cases, they're quite similar. We have an agreement in this here, but up in the top, we have some, what one can point out is that we have more igneous lamination. And I think that's part of the reason why they suggested that this G4 intruded in as a sill, producing this igneous lamination. But anyway, that's one characteristic that we have up there. And inside in the bottom here, we have a little bit of a discrepancy where Stillman says it's gabbronorites, and we say they're more olivine gabbros. But I think we do have olivines here. And I want to point out a really particularly interesting layer that we have here. We have these large olivine megacrysts that have sort of been draped, almost like snow-capped by these plagioclase phenocrysts. So some kind of differential flow between the megacrysts and the inside a plagioclase rich melt is probably what has produced this. But it's quite an interesting feature, but otherwise it is mainly gabbros, olivine gabbros. There is a little bit of orthopyroxene replacement of the olivine, but I don't think it's enough to classify it as a gabbronorite. Anyway, going further down into the bottom here, we have another discrepancy the other way around. So, but here I think our samples clearly show that we do have enstatite or orthopyroxene cumulus here, almost like oikocrysts with sort of smaller plagioclases inside, showing that these oikocryst or enstatites grew while the plagioclase were growing as well. But clearly gabbronoritic and not olivine gabbros, as Stillman said. We may note here in this section here that all the magnetite is typically interstitial, very much so, shown here in this diagram. Whereas if we go down, so there's not some kind of agreements for the rest of the sequence, but in the quartz gabbro, or we think it's a quartz gabbro, I think it is, and I don't think it's an intrusion. I actually think it's part of the layering. And inside this quartz gabbro, we find euhedral magnetites and euhedral quartz as well, which could have then been accumulating. All right, go further a little bit down below that quartz gabbro, we have some very specially textured gabbros, which have these aggregates of plagioclase crystals, forming this, for the lack of a better word, I call a plagioclase agglomerate. I'm not sure if you have a better word for it, but a very particular texture, and that's what we find throughout this section here. That's what makes it stand out. Another thing we find inside these is a lot of pigeonite or inverted pigeonites, which we don't really, or which Stillman didn't make any note of, and we don't find very much in the upper part, but we find in quite great abundance in the lower half of the intrusion. Yeah. Below this plagioclase agglomerate, we have quite a good agreement between the classification here, but all I can point out is that we get some particularly coarse-grained samples. You see the grain size here in amongst these, and some may even be pegmatitic gabbros in this case, an olivine gabbro, where you have a remnant of an olivine here, and otherwise a gabbro, clinoparxine, and plagioclase. So that's basically the cumulative sequence. Yeah, I just want to point out here again that inside this lower zone, we have again another occurrence of these plagioclase draped olivine megacrysts. Shown here is a scanned cut surface here, where you can see sort of where the olivines are and where the plagioclases have concentrated into these anophysitic pods there. Unfortunately, the thin section wasn't all that great, but it shows some of the similar features that we saw already up here in the beginning. And it's quite interesting that these two layers, very distinct layers, are formed actually almost symmetrically around this quartz gabbro here. And that has sort of led me to believe that we had this symmetrical crystallization into like a sandwich horizon there, but I'll come back to that, why it might not really work that well. Yeah, so outside along the margins, we think we have some chilled margins, quite clear, very fine-grained. Ordinary could be a dolerite, mistaken like that. And they are juxtaposed against the host basalts with amygdales and phenocrysts and stuff in it here. So that's basically the petrography gone through. Then we did some mineral chemistry on this, and I've summarized all our data, or my students did. I didn't do this, 2 students on this project. And it's just quite a nice way to compile the data. I'm not sure if this is how you do it, but it's kind of plots the cumulative frequency here just to see how big a spread does this normal distribution have, or is it how good is the data? And then you can sort of derive your averages here shown in the red circles, and you can sort of exclude some of the outliers when they're no longer along that point there. So in most cases there are averages, but with the graphs, the plagioclases, we often find polymodal populations. And then the interpretation is that the least anorthite-rich ones are the ones that crystallize from the magma, whereas the other ones could possibly be anticrystal. And, you know, to sort of support that idea, I plotted diopside against anorthite inside each sample has the same. And you can see that there is this large shift towards higher anorthite numbers here. We're suggesting that these could very well be anticrystal, whereas they would otherwise, if they were in equilibrium with each other, would be lying here on some kind of a relationship here, maybe a little bit above 1:1. The other ones, the other samples, the enstatites and the olivines, they all do lie on this sort of proportionally here, where you can say that the diopside is slightly more magnesium than enstatite, and the phosphorite is slightly less magnesium than enstatite, which is typically the case. And basically these crystallize together from the same magma in equilibrium with each other in most cases. So not very many anticrystal olivines or enstatites. So now this is the core data, the core results. So we compiled all these mineral chemistry stratigraphically or along that river section there. And these are the main results showing the averages that are not anticrystal in red, and some in the blue here are these anticrystal ones. And I'm going to focus mainly on the red data here, which shows some quite nice trends here. First of all, from top to bottom, we can see that there's a systematic decrease in the anorthite numbers, diopside and enstatite, whereas phosphorite is not much data and there's maybe not that accurate. There are some zigzag patterning suggesting maybe some replenishment there, but I think overall what we see here is a decrease in the mineral chemistry, which strongly suggests downwards differentiation or accumulation here. And I know Rice was commenting there's something wrong here, but I don't think the data I haven't manipulated the data at least. So that's quite interesting, this change here. Below the quartz gabbro, and you can see the quartz gabbro is basically a continuation of that stratigraphy. It could very well be anyway, and not a later intrusion. But below that quartz gabbro, it is not as systematic, unfortunately. I would like it to be a mirror image, of course, by these distinct layers with the megacryst, say, but that's not the case. In fact, the composition of the minerals closest to the quartz gabbro are the most primitive, and they're ranging there. It's a little bit of variation, or quite a lot of variation, but still you could say they're relatively constant up through there. And further away from the quartz gabbro, they actually become more evolved. So if anything, then he would have been differentiating downwards again. So, but then it becomes really quite strange if this was the case. But that's what the data says. Yeah, I just want to instead highlight here that this lower zone here, the compositions around here very much resemble what we have here close to the quartz gabbro on the other side. And I'm actually going to argue later that, yeah, we'll come to that later, I think, I'm not sure. I'm going to argue that this primitive layer in between here could actually be a later intrusion, but we'll come to that. We also did bulk rock chemistry here, and this is quite good to use bulk rock chemistry to calculate the proportions of minerals from a more representative sample than just looking at a thin section. And these are CRPW normative results here in a log, which basically shows or confirms, so you could say that you have this olivine-bearing upper part here, where you also have normative olivine, as well as a olivine gabbroic layer here in the basal part here, which also corresponds to the bulk rock data. And we do have normative quartz in our quartz gabbros, which is what we would expect. Otherwise, I've highlighted this black, the proportions of magnetite and ilmenite to show some very subtle variations in this. So this is exaggerated 10 times here. And you can see that these also share this downward increase in magnetite or oxides, which is, of course, what you would expect, since the magnetite was not crystallizing, it was interstitial all the way. So it would just increase in proportions as you differentiate. And below here, you could argue that we have these two-step-like variations or concentrations in or proportions of the magnetite and ilmenite, which basically very much matches up. So the more primitive the sample is, the lower the magnetite or the oxides are, and the more evolved the cumulates are, the higher the concentrations of these. But we don't have any magnetite layering or crystallization of that. Yeah, I just put this slide in just to use the bulk rock chemistry here, just to show that these are truly cumulate rocks. I don't think we should doubt that. So basically, the green ones are your olivine gabbros, and they are, of course, a little bit more to the high side here because they crystallize from melts that were parental melts that have roughly this composition in the ellipse there. So this is a chilled margin, and it's a red triangle, and then the gray diamond down here we think is one of those dikes that could potentially be parental. And so these are parental, the more primitive parental magmas that we have, around 6 to 7% magnesium oxide. And if they were crystallizing the olivine gabbros, well, they would be sort of further away because of the concentration or accumulations of plagioclase up to here and the olivine and enstatites to the other side. And then as you differentiate, these magmas would have more differentiated magmas would then have accumulated your enstatite-bearing rocks, or the enstatite crystals, sorry, in our gabbronorites. And yeah, again, with the accumulations of these minerals here. Yeah, anyway. And if you take the incompatible element concentrations in these bulk rock samples, and again, we have here in the red and the black line here at some potential parents, some primitive parents that we saw before, the same ones. And you can see that the incompatible element concentrations are much lower in the cumulate rocks, which is also what you would expect because of the dilution of these cumulus crystals and reducing the concentrations of incompatible elements. It's only the quartz gabbro that comes up in high enough concentrations, but that's because its interstitial melt is more evolved, of course. So that's how it is. But more importantly, if we plot the total amount of rare earth elements here to the right here and compare that to that of the chilled margins in the red here, we can see again that the rare earth elements, of course, are lower. But if we look at it stratigraphically, we see that they increase quite nicely systematically, reflecting the evolution by all the other indicators. Whereas, again, supporting that because, and it's not strange, because if you have the earliest incompatible elements were derived from a more primitive melt, so they would have lower concentrations. So I think these variation is due to the evolution of the melt, the interstitial melt, becoming more enriched, and eventually in the quartz gabbro becoming so enriched that even though they are cumulates, they are matching that of the sill. Had they not been cumulates, well, they would have started from the chill and gone way out to the right of the image, here, in that way, but they are cumulates. Below this quartz gabbro, we get more chaotic variations, but I do think that there is a downward increases, which is again indicating maybe differentiation down, but it's quite in cycles, 5 of them, they're repeating itself. So now this is basically all the data compiled onto one slide here, and we can clearly see that the intrusion is twofold, or divided into 2. You have an upper, very systematic downward increase or downward differentiation trends. All of this is consistent with that, all the data that we have. So that's not a problem. And there's no doubt in my mind that this intrusion did crystallize downwards, and quite substantially so. The bottom one, it just is a little bit problematic, is quite problematic. Eh? But I do think we can, I think I'm leaning towards that we have at least a subdivision of this lower zone where you have a more primitive top, and then you have a little slightly more evolved bottom of these, where although I do admit that these rare earth elements are causing me a little bit of problems with that, but I think this is what I'm going to work with. So I wanted to, we said that this intrusion was in very similar setting to the Skaergård, and why not see if we can compare it? I won't compare it in detail. I do have a slide at the end where we can do it in more detail, but I'm gonna, one thing we can see in comparison with Skaergård is that it is much more evolved magmas that the parents that the Skaergård is derived from. It has much lower mineral values. And you can see that it is more silica, even also magnesium rich, but also silica rich, possibly reflecting, as Maria said before, the crustal contamination story in this setting here. So those are the main differences there. But otherwise, actually the range of evolution in these values that we have here is quite comparable and similar to the Skaergård intrusion. Otherwise, the Skaergård intrusion is actually also a good comparison, because it is the only example I know of downward crystallization or accumulation of these, say, where you have your upper border series that crystallizes downwards. And I don't know if anybody else knows of any other intrusions where you have significant downward accumulation. Well, I'd really like to know. But if we look at this in the Skaergård, it's about 650 meters, eh? And in our case, we have at least 1,400 meters down to the quartz gabbro. And if we want to build on this, use the Skaergård as an analog for this Monetsi intrusion. Well, if the Skaergård has about almost 2.5 or more than 2.5 kilometers of layered sequence that are accumulating when this upper border series was crystallizing downwards, well, then the Monetsi would have had 5.5 kilometers of cumulates that are somewhere hidden down there. And but it is a little bit problematic, because even if this should be the case, there is a substantial layered series that we don't see exposed. Well, the upper part here is the problem. So basically, this upper part here, because it should have been the least evolved. It should be closest to these values here, but it is not. It's actually the more primitive of the 2 layers that we have here. So that's why I'm thinking that we should ignore that and think about that as a later intrusion, and rather link it up with these compositions here, which could be a mirror. But then again, it could be 5.5 kilometers below that, then that we could have intrusions if the Skaergård and the Monetsi are the same, of course. So let's see if this is possible in cross-section. A little bit realistically, here is our Stillman's cross-section here with the different units. So we've argued that there is a 1,400 meters of downward crystallization into this, what could be a sandwich horizon, quartz gabbro here. And then you had this upward layered series somewhat. We're going to ignore that upper zone there for the moment. So what we have is that just very lower part here of what could be a very deep layered sequence. But if that was the case, then it could maybe look something like this, a little mushroom shape here. And then another problem occurs. Well, where is the marginal zone here, marginal border zone? Is this the marginal border zone? But we thought it wasn't. So I'm not too happy with this model. I don't think it's probably is true. And I think the only way to find out is probably to drill through the whole sequence, if you've got the money. But this is what it could be. Instead, I've come up with this sort of model, which reduces the layered series, but maintains that we do have a sandwich horizon. So like I said before, the lower zone here has similar compositions to the gabbros just above the sandwich horizon. So I've shown it in sketch shape here, that you have your anorthite and diapside numbers here. Here's your quartz gabbro, and then we just keep that link there. And then maybe there wasn't like 5.5 kilometers down here, but maybe just a symmetrical or whatever hidden zone, much less. And maybe the intrusion was more extensive, so you don't have the problem of the marginal zone not being there. Anyway, very speculative. And then after, yeah, so that's the diapside and anorthite there. And then we need to have, I think, this plagioclase agglomerate zone there, which is quite primitive, requires that we do have an intrusion that came in after that A has been crystallized and at along the base of that quartz gabbro sandwich horizon. That's the only way I can see it, with more primitive anorthite and diapside numbers here, which is the only way I can explain the intrusions here. But I'm sure this is probably not right, but it is the best I can come up with. And if anybody can offer a better explanation, I would be very, very happy to hear about it, because like I said, I'm not an expert in layered intrusions. Then again, we have this cone-shaped geometry there, and it can be argued whether that was primary. Did they intrude like this on an inclined slope? I think Fong and Hüllingen was arguing about that in some cases, or whether this is tectonic afterwards or a combination of the two. But it's quite a substantial tilting of the layers and down sagging, if that's the case, to 36 degrees. And then erosion, and this is how we have it. So this is what I think I can say about this, and otherwise, thank you for your attention, and really come with suggestions. Thank you. Yeah.
Thank you. So I noticed in your profile, maybe you could go back to the diagram that shows the whole rock data, the whole rock rare earth data around the Noko stream. Yeah, that one. So there's one with, yeah, there we go. That's
yeah.
So what I'm noticing there is you've got the your EA number, your magnesium number of the that's magnesium number of orthoperoxine, is it you're plotting that?
Yeah, so I use diapside and acetite number. There's some comments about that, but they're all magnesium numbers.
They're all magnesium numbers. So your dye number, so that's the magnesium number of platinum peroxide.
Yes, that's right.
So what you're showing from the top down is you're showing a decrease in the EN number, but you're also seeing an increase in the whole rock rare earth content. Yeah. So could that not just be an increase in traffic content? You're just going from a more
yes, of course you could.
No, it doesn't have to be fractional precise.
No.
It has to be.
Yeah, it could, but I don't think it is. I think it is mainly reflected because in the previous image I showed you how cumulative they were away, and they're relatively equally cumulative. And if you look at the rock, I don't see this in, and it's also very systematic. I mean, why would you get a systematically greater accumulation at the top and then less and less accumulation as you go down to the quartz gabbro when you anyway have an evolution in the composition? So I mean, then I think the evolution of the composition of this interstitial belt is much more plausible.
Well,
but I
don't think your data needs that. Well, I mean, you'd have to test that quantitatively. It looks to me like all you're seeing is just a difference in proportion of the cumulus versus non-cumulus. The compositions versus.
Yeah, then from 80 to 6, it can be topic. Why should not change? That's too much.
Plagioclase core compositions, right?
Yeah, I think so. Must be. I have to still check. I've got the XY coordinates, and I want to put them onto the thin section and find out what they've actually analyzed. But I did tell them to, of course, get the course.
So if it is core compositions, then it can't be attractive.
I also find a little bit problematic with the clinopyroxene, which is usually interstitial. Right? It's not really a cumulative base, but still, it shows fantastic evolution. So that's what.
But then
that would be
the question there is: how the magnesium diffuse so fast? Those phases will re-equilibrate subsolidus anyway, so that they don't decouple. But the plagioclase will be decoupled. And so the key evidence is probably
If you look at magnesium iron in the plagioclase, that sometimes shows the exact same.
don't even think about analyzing for those things, you know, but we might have got iron.
Martin, another example of this rule which crystallizing this way from top down is of course Kiglapit.
Say again?
Kiglapit. Yeah. It also has an upper zone. But that's when I'm listening now, it's actually reminding me the Sudbury complex. I spent 5 years looking at that Sudbury stuff and still don't understand one thing, which is actually now the more I look at the data, the more it reminds me of Sudbury. You know, it's his 3 layers, major Sudbury. Norite, gabbro-norite, and then granophyte. Granophyte 3 kilometers. So it looks as if it crystallized from the top upwards, generally look like that. But if you look at the chemistry, you see that norite, then gabbronite, but granophyte itself, it's crystallizing from the top downwards, and it says 3 kilometers. So what you have 1.4 in Sudbury, it says 3 kilometers crystallization from the top downwards. I have no idea why it happens.
And you have a decoupling, it's not like a mirror image. You
No,
have something,
no,
so that would
that's
be
what-
something to.
Yeah, that was not mirror imaging. And the most involved one, actually, Gabra, which is sitting in 3 kilometers below the top. So I think that's what we need to look at, the answer to your question. Just need-
Great, thanks a lot.
What was the depth of intrusion?
I think it's shallow because it's intruding into the lavas, right? So I think it's relatively shallow, and that's one of the arguments for saying there's not a very thick layered series. Was that it was cooling significantly from the top,
Yeah.
plus it might have been heated from below, sort of preventing it. But I think that,
So that's something in common. Sudbury and this, Skagerrak, they're all very shallow. I mean, Sudbury is supposed to be a meltdown, right? So you would expect an awful lot of heat loss from the roof and therefore in situ crystallization down. It's like a lava lake, essentially.
that's why I'm thinking as well. That's enough to produce it. Although we have the bush cloud, so why doesn't it crystallize down with them? It's quite a shallow inclusion. That's not a problem.
So I have a question. Do you think that the whole system is the CO-like intrusion or just the J4? So the CO-like injection. CO.
Yeah.
For this figure, if we say the J4, they are continuing, they are completion of RDE or the mineral completion is also continued. But you think it's the CO-like injection?
I think there's a secondary injection in there with the 2 red lines here. That one there, I can, because it's so primitive, it doesn't sort of differentiate into this sandwich rise. And if I use a Skagerrak model, then I'd say there must be an injection. That's all I'm saying, although I don't like injections, still injections into later intrusions. I must say, does that answer your question? I'm not sure.
But the G4 that the original map
original, yeah.
proposed,
No,
that doesn't seem to stand out at all anymore as a separate.
so they had like a olivine rich layer sort of requiring this sequence, but I don't think we have it. I think we have a very continuous differentiation towards from the top down there. So that's the difference there, yeah. So we take away that intrusion, but propose another one down instead.
So what makes the olivine rich layer in your scenario?
So it's early crystallizing magma. So if you fill out the magma, it's very primitive, and you start crystallizing olivine, but it attaches itself on the roof and goes down, which is the problem here, right? But that's what it says, and that's
Yeah,
the
but
way.
your 4A
Yeah.
olivine rich layer.
Yeah, but that's still done, eh? So we don't agree with the VV,
don't-
how long is to the right here, right? It's just more systematic, yeah. In their case, they say it was, so in all of their cases, they say that you get accumulation of olivines at the base of the. So like a small differentiation cycles like that. Four of them, yeah. No. It's quite amazing, nobody studied this for.
Another question.
Is there any magnetic or gravity data that you use to test your hypothesis of?
I mean, there ought to be, where are the alternatives, right? There should be maybe what's quite silica, and more primitive than the Skagerrak intrusion product. Then there should be quite a lot of alternatives that we should see, but I don't think there is gravity data. I will find out. There's very little of this kind of geophysical data in Africa. So that would be one way to do it. Less expensive than drilling.
Maybe I just Bushfeld, you said Bushfeld doesn't have a chill margin at the dividend for downward crystallization. Certainly would construct. We consider, you know, sort of a 1 kilometer thick analytic or still like body of almost certainly, you know, of the Bushfeld event. And the difference, however, being that there the downward crystallizing zone is just a few, if I remember correctly, maybe 10-20 meters rather than hundreds of meters. So the other thing is, I was wondering, you know, what? So you said a little bit puzzled about the fact that the stuff is becoming more primitive when you move upwards from the bottom. That certainly could be, you know, liquid shift, right? I mean, we see that quite commonly in the intrusion that certainly the lowermost tens to hundreds of meters, you see a progressive.
So that's based on reversals by
Yeah.
So I've thought about that, but why up to the sandwich horizon, or if there's a sandwich horizon, it doesn't fit that model, and like so much reverse crystallization, but maybe if there is a possibility.
For example, in the muskrats in the Wingelina, the basic reversal is something like 300 meters, so I think.
Because it goes so far up into the intrusion, sort of like if you look at the intrusion as a whole. And you still would have then exclusively downward crystallization about that reverse base of reverse. There's no layered series at all in between. Or normally differentiating layered series. There is something wrong here, but anyway.
Okay, so we can go then to coffee and tea. Just to remind you guys, there is the poster room on the second floor. Benjamin can show you where it is. If you don't know and you have questions, put up your posters, whatever you posted, you can put up posters that you were meant to produce tomorrow during the main symposium. You can already put it up now, there's enough space. There are little stickers, sort of Velcro stickers that you can use to attach your poster to the boards. Yeah.
When should we meet again?
So yeah,
In 1 hour or
the plan was originally at 11. So we have a bit of extra time, of course, unless we want to have a slightly longer lunch.
But remember, this clock is 1 hour behind. Behind. It's 10:30.
Then it's just picture.
So we can meet 11:30. So we have 1 hour now.
Let's say in the middle, 11:15. So just the last word.
So what time once again?
11:15.
11:15.
Yeah.
Okay.
Okay, I'll pause the recording so we can
Okay.
restart the same recording process.
Okay.
Okay.